Hi, everyone. Welcome to season 5, episode 1 of Additive Talks. So, for those of you who are joining us for the first time, make yourself comfortable. Additive Talks are simply a series of panels that focus on discussing the use of additive manufacturing technologies in a given industry. If you've been there before, thank you for listening to our insight into the world of additive manufacturing. My name is Katie Sinze, Managing Editor at 3D Adept Media. Today, we are going to talk about safety, aerospace 3D printed parts, their roadmap to safety. Safety is a big topic for the industry. And before we dive into this topic, I would like to give the floor to our amazing speakers around this virtual table so that they can introduce themselves as well as the company they represent. And I will start with Svenja. Good afternoon, Svenja.
Good afternoon. Hello, everyone.
So maybe Svenja, can you just tell us a little bit more about yourself and Liber Aerospace Technologies that you represent?
Yes. So hello, everyone. My name is Svenja Pastotnik. I'm the head of additive manufacturing at Liber Aerospace in Lindenberg. Lindenberg is located in southern Germany, close to the borders to Austria and Switzerland. And Liebherr is producing landing gear and flight control systems for aircrafts and helicopters. In my role, or as a team, we are responsible for our additive manufacturing activities, starting from research and development, product development, and support of series production. And before joining Liebherr 2 years ago, I was working in several AM-related roles in the space industry.
Thank you very much, Svenja. What about you, Dr. Folgan?
Okay. Hello. First of all, a good day to everybody, and thank you very much for having me here. So I'll be doing a short introduction now. So my name is Wolfgang Kaufmann. I'm working since 25 years at the airworthiness authorities, and especially for 20 years at the European Union Aviation Safety Agency called EASA. So I'm working there in the aerospace certification area for large aircraft, and was involved in the past time, so in various projects. So Airbus A300, A400M, and A350 freighter, and so just to name a few. And so I'm being involved there in large airframe aircraft structures for certification purposes. And I'm also focal point for some new technologies. So, for example, I was a former focal point for the additive manufacturing technology. Well, so to say, we have to admit the industry, the aircraft industry, approached the airworthiness authority with this new technology when they've had already gathered 10 years of experience with this. So that was, I think in 2015, they approached us the first time. And then we started the first, so we initiated the first meetings to get all important parties together. That means airworthiness regulators, FAA and EASA, of course, then the aircraft manufacturing industry, the technology providers with the 3D printing, and also the feedstock providers with the metallic powders. And so we got everybody together and try to find out what is the most important thing to look at when we would like to certify 3D parts. Yeah, so this is the main thing what I'm doing here at EASA.
Thank you very much. What about you, Brian? I think this is still the morning on your side. So good morning, Brian.
It is. Yeah. Hi. Hey, everybody. My name is Brian Bachman. I work for Honeywell Aerospace, and yes, I'm based in Phoenix, Arizona. So it is 6:34 a.m. here. I have been at Honeywell for almost 19 years now, and I started my career working in additive manufacturing here at Honeywell, doing directed energy deposition for our repair and overhaul business. And over the years, I've held lots of different roles. And I think I started working with laser powder bed fusion back in the late 2000s when it was very, very new. And then Honeywell, after some years, we decided to invest and bring a lot of those machines to our factory here in Phoenix. And I managed that factory for several years. I'm currently a chief engineer for our mechanical manufacturing. So I deal with all types of manufacturing across all of our global factories, mostly on the mechanical side. So I touch a lot of different areas, but I've always been very involved with additive manufacturing and implementing it into our production factories.
Yes.
Thank you.
Thank you very much, Brian. A quick reminder for the audience. So, please, if you have any questions, use the Q&A chat, on your screen. We will take a break in about 40 minutes to answer all of them. If you have any remarks, please feel free to share them as well in the Q&A chat. We will read them, we will comment. This is a safe place, and feel free to share any insights you have into this topic. The most important thing is that we can learn from each other. So let's dive into the topic. Brian, my first question is for you. From an industrial standpoint, how does Honeywell integrate additive manufacturing into its production workflow while maintaining compliance with aerospace standards?
Okay, thank you. So I think that there's a lot of pieces to that question, obviously.
Yeah.
Yeah.
So maybe
Okay.
just try
It's
a big
kind of,
overview.
yeah, a little profound. But I think the first thing is that we have to recognize that you have to have a good foundation to bring a new manufacturing technology into a production environment. And what I mean by that is, like, you have a good quality control system, you understand the elements of process control, and you have that culture of driving adherence to that process over time. And I think that's really important if you want to adhere to aerospace standards, this new process. So, at Honeywell, we've been making production aviation parts for decades and decades, right? So we had a pretty good foundation. We have a good foundation, a good quality system. I think with additive manufacturing, the hard part was putting all those pieces in place to insert it into production. And what I mean by that are the understanding what the process is capable of. Because when we first started inserting into production, there were no industry standards, there were no specifications, nobody had material data that we would consider design allowables for aerospace, right? Which is really important. And so we had to create a lot of that ourselves. We had to work inside a prototyping environment and understand what the process was giving us, what it was producing in terms of material quality. And we had to create our own specs, create our own design allowables. And once we had those, we were able to insert them into our existing production system, right? We had that foundation, and we know the important elements of process control in driving that quality, that adherence to standards, which is really important, and I think probably the most important part of maintaining aerospace standards.
Okay. Well, good introduction. Maybe Svenja will follow then. Svenja, before its history of additively manufacturing aerospace application, Liebherr Aerospace and Transportations remains the first tier provider of onboard solutions in the aerospace industry. Can you tell us how big the differences are between certification of 3D printed parts in aerospace versus certification of parts traditionally manufactured?
Yeah, sure. So I think with respect to certification, the differences aren't as big as one might think.
Okay.
For example, the first thing you have to think about is always the criticality of the part, and that mostly determines the certification and the amount of testing you have to perform to qualify the part. So basically, for qualification testing, it's mostly the same that we do for conventionally manufactured parts and additively manufactured parts. The key challenge, however, that we have at the moment with additively manufactured parts is, first of all, what Brian already touched upon, the lack of standardization and material data, design allowables that you usually have for conventional parts. So there's still a knowledge gap on many sides that you have to close during the development phase and qualification phase of a part. So a lot of times you have quite in-depth discussions with your customers, materials and processes department, stress departments, because oftentimes you have new people or people in the team on the customer side who have never worked with an additively manufactured part before. So sometimes they might think of the 3D printers, from home applications, FDM printers. And this is the way they think of additive manufacturing, polymer, maybe brittle parts. And so a lot of the work that has to be done is provide the confidence to the customer that we have a robust, stable process. And that's, I guess, the main challenge or the main difference as well between conventionally and additively manufactured parts.
Well, thank you, Svenja. And the good thing is that, well, to discuss this topic, we also, have on this virtual table somebody from EASA. And Wolfgang, the role of standards development organizations and regulatory and certification authorities often seem to intertwine. Could you clarify the differences and maybe give, the audience a general understanding of EASA's activities?
For sure. So first of all, I would like to say that it's really great that we have Svenja from Liebherr and Brian from Honeywell. So the parts manufacturers, the people who are working with the machines, they know how it goes, and they are the experts. And for sure. So we are collaborating with standardization and accreditation organizations such as ASTM International, SAE, or NetCap, for example, for accreditation programs. And we contribute in those working groups by sending members from EASA to participate, and which focus on specific technical topics. So here the AM, that we have lots of topics. We have the feedstock material, can we use it again, or whatever. And our involvement shall ensure that the development of standards also addresses our aviation certification requirements. We have mainly here addressed the 25613 for materials. And that's a very important requirement, and we have to be sure that this is properly being addressed during the development of those standards. For that reason, we are participating. And again, it's really important to note that the industry, including aircraft manufacturers and suppliers, also contributes to the working groups, and as they are the true experts, and their input is really essential and invaluable. This is really very important to say. So we are just the authorities. Well, we have some requirements, and we have to work according to this. But the technical people, they would have to cope with this as well, and they have to have the understanding why we are going to use these requirements and to request this from aircraft manufacturers. So ultimately, when those standards had been developed with our cooperation, we are accepting them and referencing them in those agreed standards in our aircraft certification requirements and or the guidance material.
Thank you very much. Thank you very much, Wolfgang. Svenja, and the same questions will go, to Brian as well, but I would like Svenja to answer first. Svenja, large OEMs and their major supply partners are often safe to have the required resources, such as qualified personnel, equipment, procedures to achieve qualification and certification of parts in-house. How does that expertise translate into your activities? So it's good to have, like, the different experiences, from Liber and Honeywell right now around the table. But I would like to start with you first, Svenja.
Yeah, so basically, we started out additive manufacturing in 2009, 2010 at Liebherr. And I think the crucial thing for success was that a core team was created. So we have a so-called technology incubator for additive manufacturing, and we have a core team with all the relevant AM specialists being together in one team. So we have the expertise for design for AM, for defect evaluation, NDT, the process itself. We have everyone together in one team, and that was a really crucial factor in being successful in going into development and serious production with additive manufacturing. And this team still exists. So basically today our main tasks are continuous improvement activities, but also the rollout into the other departments in the company. For example, if we are talking about serious production in the very first months and years, it was still the AM core team that was doing the serious production tasks. And now this is in our just general production. So yeah, everything started off with the AM core team and is now being distributed into the different departments in our company.
Okay, good. Brian, very quickly, how does that experience translate into your activities?
Yeah, I think it's very similar. I mean, it's really important that we have the right personnel because this is a process, right? It still requires observation to make sure that it's working as intended. Whether it's through the inspection or the operator setting up the machine, they have to understand what is, what is a good outcome and what looks good from a process standpoint. When you look inside the window of the machine, you need to know, hey, is this what is expected or not? So it's very similar. And then I think, the other point to your question about, having machine qualifications in place is another element, right? You need to qualify every machine that we have, right? Even by serial number. And it's not a trivial thing because we try to test the whole space of that machine out. And we have standards and specs for what that material, what that machine qualification should require. And until you have the personnel and the machine qualified, we do not allow you to go and qualify parts. So you need to have those elements in place before you qualify parts.
But then, Wolfgang, what about smaller organizations that do not often have, the resources to have such type of expertise in-house? Do they work directly with EASA? Or, how do they proceed according to you?
Well, it depends. So the thing is, it's fully understandable that smaller companies would like with this technology to expand their product portfolio, of course, because it's on the first glance quite easy, just printing something. But it's not so easy. So we have two options in the European system. So you may qualify and for a design approval or a production approval or maintenance repair organization approval. So this is a whole procedure they have to undergo with the EASA, and they have to develop a handbook. But when they have this, they can really approach, for example, with such a 3D machine, a printing machine, by take into account all the necessary requirements. So that means qualification of the machine, like Svenja and Brian already told us. They can do this, and then they can produce approved parts according to our aviation requirements. But this could be a bit too costly for small companies to approach or to get a design approval organization. And so for that reason, they could just be a non-qualified supplier in combination with a DOA approval holder. That means, for example, when you have a huge DOA approval holder like Airbus, for example, you could, as a non-qualified sub-supplier, being subcontracted by this company Airbus with a DOA approval, and they would be doing audits, and the non-qualified supplier would be under survey of this DOA, that they have to produce parts according to the requirements and the aviation strict requirements which we request from them. So they would be under survey as a non-qualified supplier. That would be the cheapest solution for them, for the small companies. Okay.
Okay, good. Brian, when we talk about qualification and certifications, we usually mention machine and material qualification, DFAM, fatigue, or even damage tolerance, as key areas that require qualification and certifications. How do you prioritize your efforts at Honeywell? Does each of these qualification areas need to be met before production?
So yeah, I mean, generally speaking, you need to qualify the material before you can qualify the part. Yeah,
right.
I think, and like Wolfgang was saying, a lot of people can just print a part. You can be ready very quickly, right? But we do need to have that upfront testing of the material along with the parameters that you're going to be using, the machine type, and all of that. We need to have that defined, and it needs to be documented and controlled first.
Yes.
With respect to fatigue, right? That element of testing, that's going to be determined based on what is needed from a part application environment standard, right? So if the part is exposed to fatigue loading, then yes, we need to go get that data. We need to establish the design allowables for that, right? So really it depends on what that part requires, and that will dictate how much material data we need. But getting material properties is not a trivial thing, right? It's very expensive to get this data. Okay. Millions of dollars, right?
Yes.
And so what we tend to do is we try to find multiple applications
Yes.
that can take advantage of a material before we decide to characterize it.
Yes.
And then we understand, okay, what data do you need? What data does this application need?
Yeah.
And then we set out to try to get 80% of that data right off the bat. And then the remaining data needed is going to be done during your part-specific qualifications, right? You're going to get all that. Damage tolerance is another very complicated topic. Not every part requires damage tolerance, right? And if your part requires damage tolerance, then that's definitely going to put it in the very top of critical additive parts being printed for aviation.
Yes. Okay. Svenja?
Yeah, I think the answer will be very similar. So maybe.
But then, speaking of applications, maybe are there applications where certifications are more challenging, for instance, than others? If you look at these different areas that have just been mentioned, and and the importance of the application in the process, do you think there are applications that are more challenging to certify compared to others?
I think again it's determined by the criticality of the part, and then it doesn't really matter whether it's an AM part or a conventionally manufactured part. For example, we are authorized to produce class 2 and class 3 parts with additive manufacturing at the moment. So for criticality class 1 parts, we don't have the authorization at the moment to produce those. And then, of course, other material data would have to be produced. But for example, on our side from 2015 to 2017, all we did was industrialization and process qualification. So, and of course, since then, we do regular revalidation build jobs with, the samples everyone knows, fatigue, tensile. So the amount of data that we have by now is very large. And this also boosts the confidence on the customer side, of course.
Yeah, correct. But then, Wolfgang, how does the process work on EASA, side? How do you approach the validation of AM technologies compared to traditional manufacturing processes?
Yeah, okay. I possibly would have to start with the thing. Additive manufacturing seems to be quite easy. Buy the machine, print something which looks nice and shiny, and then bring it onto the market. This is the danger, right? And this is where Brian and Svenja are talking of, to produce allowables, data allowables, and to have to qualify the machines so that they have a certain repeatability of their product, of the parts. And that means also the repeatability of fatigue properties. There are lots of processes involved for the fatigue properties, for example. So you print layer by layer for the powder bed fusion, and you may have to have a kind of post-processing afterwards. So we call it hipping, for example, hot isostatic pressing, just to get rid of the void. And that all can change your fatigue property. So it's really complicated. That's right. So, but we don't do it in a different way like we did it in the past for welding or castings. So we also had lots of meetings in the past where we just set casting factors or something. And so you have to talk about the topics. That's the point. Additive manufacturing is a bit more complicated, but you have lots of opportunities. You can do weight saving with topographic design. And this is a dangerous thing. A company can print a part, and they even can print a part number onto the part, so that it looks like a real one, but it's a bogus one. And this is the danger. You don't know if they hold the right parameters for getting the right fatigue properties, for example. And this is a danger. And for that reason, the DOAs, for example, Liebherr Aerospace, they have DOA and I think also POA, so Qualified Organization for Aviation Parts. They know about this, and they know how to qualify the machines, and they know that there's quite a lot of work behind this. And the same with Brian and Honeywell. So those companies know about the processes which are necessary. But small companies, this is a danger. They may not know it, but they can print such a part. They just need the file, the printing file, right? And then they can print it, and nobody can look into it if it has got the right microstructure. So that's a problem. And we do it's all about safety. So the material quality should stay the same. It should not go down because of possibly people who are producing non-certified bogus parts, which look the same like an original one, but they have different properties. This is the danger.
Okay. Well, I want to discuss a practical example before we move to the Q&A chat. And I remember that I think recently the most recent coverage we had on 3D Adap Media was the one of a metal 3D printed flex shaft, a component with a high degree of complexity produced from titanium by Liebherr. that was approved by EASA. So I was wondering, Svenja, the key challenges you faced, during the process, during the certification process.
Yeah, I think I have to repeat myself here a little
Oh
bit.
my goodness, I'm so sorry. I thought you were going to share something different, but would you like me to skip that question?
Well, again, I think it's all about the stakeholder management.
Okay.
And maybe another challenge, but this is not related to the part itself, but in
Okay.
general with additive manufacturing. At the moment, we still have a quite limited supply chain. Wolfgang was just mentioning the HIP process. There aren't too many suppliers out there who are qualified to do the HIP process for aviation purposes. So with more and more parts being produced by the tier ones, of course, we are all basically using the same suppliers. So there is definitely, yeah, a challenge at the moment, and area for improvement to just have a more vast supply chain. I have the flex shaft here for people to see. So this is a conventionally manufactured part. It was conventionally produced by 8 individual parts that had to be integrated. And now we have our additively manufactured flex shaft, which is printed in one part in the middle. It can move, so it's basically 2-in-1. And this is, I think, a really nice example of what you can do with additive manufacturing and how you can really take out the benefit and just do functional integration. And this is really what AM should be about, to generate benefit.
Thank you very much, Svenja. But then my question is a little bit different than for Brian, because I remember that, well, about 4 or 5 years ago, Honeywell Aerospace achieved FAA certification for a 3D printed flight critical engine component. But then the component was still produced via metal, 3D printing. And I was wondering, why do we have this continuous focus on metal 3D printed parts, especially, and not polymer, for instance?
Okay, yeah. So a lot of our products at Honeywell, we find challenges with the metallic material supply chain, getting castings, getting forgings and sheet metal parts, right? So we tend to, kind of end up on the side of we need additive for metallic materials more than we do need polymer. But, honestly, if you could give me a polymer material that mimics the properties of metallic materials, I would choose polymer because everybody wants to save weight and cost, right? I mean, metal is more expensive to print than
Correct.
polymer materials, right? Absolutely, right? I mean, I know we had an application on one of our engines very recently that we designed to be polymer. And we actually put it on the engine to test it, and it performed amazing. It really did a great job.
Oh.
And then after the testing, engineering came back to us and they were like, well, the max temps are going to be just above the glass transition temperature for that polymer. And so at that point, it was like, we have to move into metals, right? Because the part and the application and the environment that the part was in, it forced us to use that. So I don't want to say that we absolutely always focus on metals over polymers. It's mainly the application that
Yes.
forces it to be that way.
Okay. Let let's pause for a minute. Let's try to answer questions from the Q&A chat. One of the first questions is actually related to the question I just asked. It's about different additive manufacturing technologies. That question is from Steve. Are there specific AM technologies, e.g., LPBF, DED, binder jetting, that present greater challenges for certifications?
Hmm. Um, is that for anybody, Ketty? You know?
Well, yes. If
Yeah.
you if
Okay.
you, if
Okay.
you feel like you can answer, then I will gladly give you the floor, Brian.
Uh, well, I'll kick that one off. I mean, um, I think, based on my experience, because I have experience with all three, and we do work with all three. I think,
Okay.
for me, DED presents a pretty big challenge, mainly because as you build up geometries, uh, the part material properties are a little bit more influenced to they're more prone to changing because of the heat transfer that we get, right? So with laser powder bed fusion, it's a small melt pool size, it's a quick cooling rate, right? So we tend to see very stable material properties, even if the geometry is changing as we print it upwards. Whereas with direct energy deposition, you have a lot more heat going into the process.
Yes.
Um, but again, that process is evolving to where you can put down very little amounts of heat and you can control that microstructure a lot better. But it does have the potential to be more manipulated than others, at least
Yes.
on my experience.
Okay.
Yeah, maybe
Base.
from
Well,
our side, we are investigating and having R&D activities in place for DoD and binder jetting. But
Okay.
in series production, we are only using the laser powder bed fusion process. And from my experience, this is also the one where most activities, also with respect to standardization,
Okay.
are most advanced. I think most of the time, DED is always considered as well. But a lot of the standardization efforts at the moment are still targeting the powder bed fusion processes.
Yeah. Yeah. I
yeah,
was
c-
thinking the same. Yeah. Wolfgang, I
correct.
think you want to share something.
Yeah,
Yes.
well, I may add something. So, for example, well, each of the methods have their pros and cons. For example, for
Yeah.
the DED, you can do large geometries. You can do repairs, and on large geometries, and so yeah, of course, the heat transfer is different, so compared to laser powder bed fusion, and
Yes.
but each of those methods has got its right for existence, let's say, and so it depends what you want to do. That's the
Yeah.
point. And just because of the because you mentioned the composite structures, polymers.
Mm-hmm.
Well, I can tell you this is coming up. So there are some research projects here on national basis on European areas. So from
Mm-hmm.
some aircraft manufacturers who really do this extensively within the research.
Mm-hmm.
And so that comes to, let's say, recycle of the material,
Mm-hmm.
reuse of the material, and this is also for metallic the case. That comes. So there are some really specific investigations going on this area. And so to say, for the metallic, the 3D printing started, I think, more or less in the industrial area with metallic. So that was mainly nickel base alloys, which are being used in engines and hot
Mm-hmm.
parts. So, for example, 718 Inconel, so this is typical one, or the titanium 64, right? So those are the materials you can print really excellently.
Mm-hmm.
And then if you would like to take or to use the typical airframe materials like aluminum 2024 or 7075, they have some problems with the feedstock materials. So they are hygrophobe, and
Mm-hmm.
they, let's say, suck water, and you have to
Yes.
keep them dry. And if you want to, well, they are working on this, and I think finally they will get a solution for this to
Yeah,
cope with this
correct.
material. Well, but there are still some issues to solve. I
Yeah.
wouldn't say that they never able to solve. No, our industry worldwide is perfect, and they have good engineers. They want to
Oh,
have problems to solve it. They solve it finally. That's our experience.
thank you. Well,
Okay.
Question number 2. Can digital twins and simulation tools streamline the certification of additive manufactured parts? That's a tough question. I don't know who
For who is
wants.
that question? Okay,
I'm not sure it points out to a specific expertise. So maybe Wolfgang, if you have certain experience.
I suppose it's more going to the industry side. So for
Yeah.
digital twins, yeah, well, I cannot say so much on this. So we didn't encounter this up to now. So it's kind of going into the area industry 4.0, what we have in Europe here, and that you try to simulate the manufacturing process by simulating structures and the twin of the product or of the part which you're going to produce, and by implementing all kind of possible flaws and whatever. So it's complicated.
Yes.
But if it's working, so it's finally a good tool, I think, for improvement of the production. Yeah. So for sure.
All right.
Yeah, I think.
Brian? Yes.
Yeah, no, I think it's really hard for certification purposes, right? You need so many possibilities and scenarios and defects that you have to consider. It's a massive machine learning thing that you would have to do for certification.
Yeah.
But when we're developing the process, right? Developing the process, understanding how to print a part and account for the distortions that happen when you print it. It's a great tool. We use it today, right? We do tons of simulation to understand how to print a part so that what we print meets the dimensions that we want. That is very valuable, and we do that. But certification, we still have to test it the traditional method. Yeah.
Okay.
Yeah, there are a lot of activities going on at the moment, especially with respect to in situ process monitoring and investigating how the in situ process monitoring data can help to reduce or maybe in the long run substitute traditional NDI methods. But yeah, as I said, it's still in the development phase. But a lot of activities are going on with this respect, also together with EASA in the working group 3 that they have started in the context of the AM working groups.
Yeah. Well, question number 4. Number 4 from Brian. From Bram. Sorry, Bram. Sorry, Bram. Our additive manufacturing is a fast-moving field. That means there are a lot of process and technical developments. But what with those new technologies? How are those validated? Do they stand a chance for short-term use? And what in technologies where they combine materials? Bram, I'm not sure I understand the last questions. And then how would you go about validating this? I think that's a question for you, Wolfgang, right?
Well, I found so
number 4.
Number 4. So this one. So you mean about the
from Bram
complexity of AM process?
Yeah.
Okay, that one. So if it stifles innovation, you mean that one?
No, I'm still in the Q&A chat. I'm reading question number 4 from Bram. And I think that question is meant for you.
Okay, could you repeat it, please?
Yes, let me just try to read the question one more time.
I just see 3 questions displayed here in the chat.
I think if you go up,
okay.
Yes, if you go up, that will be the first question. But let me read it for you.
Yeah.
Additive manufacturing is a fast-moving field. That means there are a lot of process and technical developments. But what with those new technologies? How are those validated? Do they stand a chance for short-term use?
Yeah, this lives and falls, let's say, with the criticality of the part. So when it's really a part which is critical, so that means once the part fails, it's hazardous for the aircraft to get a safe flight and landing. So you would really have to do a lot on this. So you would have to have a kind of certified organization like Honeywell or Liebherr is, and you have to follow all those processes which you have mentioned already. So for machine qualification, material qualification, process qualification, so stability of the process, repeatability, everything of those points, of those parameters has to be in the right area. Otherwise, you're not being able to produce part with high reliable properties due to fatigue and structural strength. So this is the point. And this is always then very difficult. So you have to do a lot of certification. This is not business for small companies without any certified organization. So for sure not.
Wow.
Yeah, but we still even to get it into production, that's a lot of work, absolutely. But we do take advantage of these newer technologies on a prototyping basis. We do a lot of development to understand what they're capable of, being able to take some of those processes that combine two different materials together. Really, on our advanced technology side, we're experimenting with what we can get from those newer technologies. And then I think the key is if you can identify applications that take advantage of those newer technologies and justify the amount of testing certification that you have to spend to bring it into production, then that's the key. You got to find those opportunities.
Yeah.
And the other key parameter from airworthiness authority side is we don't want to have a drawback in safety level. So that means if you're producing a part, and with a new technology, we should be sure about the quality of the part. And it's not acceptable just because it's difficult and complicated with these parameters you have to fulfill. It's not acceptable to have a drawback in safety level. For sure, this is the point.
Yeah, it definitely starts with a good business case for those kind of new technologies. And then this also needs to be a frozen process at some point to be able to qualify it.
Yeah. I think I know by the name. I think I know where Bram is coming from. I think he's coming from selective powder deposition, so multi-material 3D printing field. So maybe that's the reason why he asked these questions. By the name, I think that's what I can say. So I hope your answers have been useful to him. So yeah, question number 5 from Frederick. Would you say the current state of the art is rather certifying a specific process, or is it more the validation of a single part within a specific process? And what needs to happen to make a 3D printing technology gaining the same status like other conventional processing techniques? And Frederick adds, I'm coming from polymer pellet extrusion, so large format additive manufacturing, and there are a lot of factors affecting the final part quality. So that's question number 5 in the Q&A chat.
Maybe I can start on that. So from authority side, so we are proposing a performance-based approach. That sounds really weird, huh? So I try to explain that one. So that means you don't have to do all these difficult and cost-effective and time-consuming qualifications for all parts. So that means the first thing you do, you make an assessment on the part, how critical it is. For example, the famous coat hanger. You can print this one, and you don't have even to, well, let's say you print it out of metal. So you just print it and install it in the aircraft, hang the coat on this, and what happens when the part fails? The coat falls down. That's it. So this is a non-critical, typical non-critical part. For this one, you don't have to do at all those difficult, well, let's say, I would say qualification for the machines, but when you just turn over to the critical ones, where the failure of the critical part would be hazardous for the aircraft, then you have to do this, of course. So that means from authority side, we ask the part manufacturers do an assessment on criticality, and then we see how far you have to go with your production process and the qualification and so on. For non-critical parts, for sure, the coat hanger, you just print it and install it. That's it. Even when it's metallic, no flammability requirements to be assessed. So this is quite easy one. So it's depending on the criticality of the part. That's it.
Does Brian or Svenja want to add something else to this question, to this answer?
And I think, the second part of that question was, what is it going to take to get additive into the same as conventional, right?
Yes, correct.
When it comes to qualifying. And I've asked myself that question tons of times, and what I keep coming back to is history, right? I mean, we need more parts in the field with history that have proven success records, track records that we know we can rely on this process. I mean, if you look at castings compared to high quality laser powder bed fusion, castings have a lot more issues, right? There's a lot more problems that come out of castings than laser powder bed fusion parts from what I've seen in the past 15 years, okay? And that is true. But why do people, when you say, oh, I'm going to make this part out of a casting, they don't bat an eye. But when you say, I'm going to make this part out of additive, they start freaking out. And it comes down to history. Castings have 50, 60, 70 years of experience on aviation parts, and they have that history. And additive does not have that right now. And so the more efforts by people to qualify parts, to put them in a production aviation environment, we get that history and we can build that foundation. It's that, to me, that's what it's going to take.
That's correct. May I add something as well on this? Due to the performance-based approach for the requirements, as Brian said, when you have a history on a part, so you can really use this as well. For example, when we have multiple load paths in some areas, we have, let's say, for a cargo door latching and locking mechanism, we have those hooks, and you have 10 of them, and 3 of them could fail, and it's still, from structural integrity side, safe, the aircraft. So then you could go and the approach and just replace 3 of the original conservative manufactured parts, do it by additive manufacturing, and then you put a specific inspection on top of this, and then you see how it is behaving during operation. And when you're lucky, you see, well, that's not much different compared to the others in conventional manufacturing wise. And so then you can really, in small steps, going forward to say, okay, we have done this experience, and we can replace some more parts of this, and this is well, the risk-based approach.
And I think it's also really important, and it will just come naturally, that with more parts in the field, more people on every level and in every field of expertise will get to know additive and know that the process is just like any conventional other process, a safe process to use.
Yes.
Yeah. So from my side, the final word on this. So, what is a very important thing is to keep the electronic files, the printing files, somehow safe, so that they are not going to be copied from some people, and they are just using those parts. And this is really so. They have has something to do with cybersecurity as well. So when people are stealing those
Yes,
printed files and those print files,
that's
and
a huge topic.
just
Yeah.
print something. Yeah, exactly. So they have the geometry information, but
Yes.
not the material one. So this is something else. Huh? So
Yes. Yeah. Thank you very much, Wolfgang. Before we wrap up, I just want to ask the presenters if they have any questions for their co-presenters. So that's always something that we used to do. And we have 5 minutes left. So does any of you have a question for the other?
Brian, maybe a question to you. How many different products do you have in serious production at Honeywell at the moment?
So we've qualified. I can't get into exact numbers, but let's just say we've qualified probably over 25 parts for production applications. And we have suppliers making some of those parts. I do internally. We try to keep our internal operations with a certain amount of production and a certain amount of prototyping, right? So we can continue our development applications. I know that we serial production internally is going to be about 5 part numbers, right? And that keeps us pretty busy, right? And then we have other part numbers that we work outside of Honeywell with suppliers, right? But I wish it were, 100 or 1,000 part numbers. I wish I could give you a big giant number that would blow everybody away.
Well, I think it's already quite impressive.
Yeah.
Yes, I will say so. I will say exactly the same.
So, Brian, may I ask, so which are the main parts you're producing? So is this for engines or for auxiliary power units or?
So they are for engines, right?
Yeah,
And
okay.
it's a mix, right?
Yeah.
Propulsion. We have some qualified APU parts, but they are not. I would not call them serial production, right? Actually, I did that back. We do have one serial APU production part. Yeah, we do. Right?
Are you doing also these famous fuel nozzles which are being produced by GE? This is one of the parts. Well, the engine has got several of them, so this is one of the
I
things.
know.
It's risk-based approach again, and so they've printed them and some of them, and they are quite reliant. So they are quite okay in operation. So they don't have any problems. But okay, I think due to the geometry, they have small channels there. So one thing is when you produce it via powder bed fusion, so you have to get rid of the powder. Then this is a problem. So get it out of the small channels. And possibly one other interesting thing is, I think, how was it? The passport engine? No, was it passport engine? No, the engine, turboprop engine, which was, I think, designed by GE. It had a former, just to give you an idea on the possibilities, a former number of parts, a whole engine of 850 parts. And then they've integrated everything, also the gearbox and so on. And they ended up with 12 parts, I think, finally. Something like this with the additive manufacturing. Whoops, it was really
impressive.
quite surprising, yeah. And so if such a process is stable and you can get rid of the powder in all corners and so on, it's really something you can save money and by producing this part. So this and possibly one last question to Svenja. I know about. I think I've read something about actuator housings. So you're going to produce as well via AM. AM, is that right? Or
we have development activities on actuation housing, and we have another development activity actually that's currently in qualification of a manifold. So that will be our first hydraulic component. And maybe as a teaser, if you are going to be present at the Paris Air Show this year, you might want to have a look at our booth. And
okay, but you will still be coming towards us for the certifying of the parts, right? Or
yeah, that's already ongoing. Yeah.
It's already ongoing. Okay, so it's well, I'm structures. It's not my expertise in that area, possibly. So it's all the hydraulic guys. Okay, but interesting.
Well, thank you. Well, it's time. Thank you very much. Thank you, Brian, Wolfgang, Svenja, for joining us and for kicking off this season of Additive Talks. Thank you to the audience who have been following us for 5 years now, and for listening to our insights into the world of additive manufacturing. The next virtual panel will be announced soon. And I hope in the meantime you will stay safe, you will follow us on social media, and you will keep a track of this panel, whose recording will be published very soon on our online media. So that's it. And stay safe and stay tuned wherever you are in the world. Thank you so
So,
much.
well, thank you very much. It was a pleasure to have the talk with you guys. Thank you.
Yeah.
Thank you.
you.
Bye. Have a good
Bye-bye.
day.
Yeah.